Hi, good morning to everyone. I'm Dr. S.A. Sivashankari. Today's topic is conversion between number systems. After completing this session, you will be master on these four skills. The skill number one, which is the number system and positional weight. The second skill is decimal number system to binary, octal and hexadecimal. The third skill is binary, octal and hexadecimal to decimal system. The fourth one is binary to octal in turn hexadecimal. These four skills, wherever you have some rules to follow, we will check over the examples, how the problem to be solved, and I will discuss you the fast shortcuts also. So, number system and positional weight. In your module 18, we discussed what is a number system and what are the positional weight. So, number system is nothing. What is a number? Number in the sense, those are the framework of the mathematical system. So, the number which is applicable in engineering, computer science, as well as the mathematics. Next, it is a positional weight. We already discussed the number system or broadly classified into two types as a positional number system and non-positional number system. So the non-positional number system which actually loses the weight, but if it is a positional number system, we used to call it as a weighted number system. Next one, there itself we discussed what are the types there in the positional number system. Decimal, binary, octal and hexadecimal. So decimal, which is of base 10, binary, which is of base 2, octal of base 8 and hexadecimal of base 16. And you can do the conversion from one number system to another number system. I mean all the binary, octal and hexadecimal to decimal, and you can able to do the conversion from binary to octal, hexadecimal and shortcut. This is a number system overview, what we discussed in the earlier class. You can see the system is binary, base is 2. Base 2 represents that it is having only two unique codes. The unique codes are zeros and ones. I specified it as a digits used. I have given the example as 1011 base of 2. Means that binary is a combination of zeros and ones. 2 represents the base or radix. So next it is octal. Octal means it is a base 8 or a radix 8. So means that 8 unique symbols are available in the number system. So the digits used are 0 to 7. I have given you the example as 157 of base 8. So you can check here 157 are the numbers available between 0 to 7. Next one, it is a decimal. 10 means that the unique symbols are 0 to 9. I have given you the example as 347 base 10. And the last one, it is a hexadecimal base 16, 0 to 9. Instead of 10 to 15, it is as A to F. So I have given you the example as 2A, 3F base 16. You can check there. Two alphabets are available there, A and F. Right. Okay. How to find the value of every digit? That also we discussed in the last class. How we are doing that? Summation of di into r power I. So what is the di represents? It is a digit. What is that r power I? R represents the radix or base. Power of I represents the position. So position counts up to left to the radix point as well as right to the radix point. So you can write n is equals to dn minus 1 into bn power minus 1. That goes to d power d1 into b power 1. So d represents the digit, b represents the base. D power 0 into b power 0 dot d minus 1 into b power minus 1 d minus 2 into b power minus 2. This also we will be recollect while doing the program. The first section is decimal to other bases. One short and fast shortcut I will tell you. See, if you want to convert the decimal to other bases, you have to do the continuous division or else the repeated division. So you have to do the continuous division or repeated division by using the bases. This is applicable only for the integer part. If you want to do it for the fractional part, you have to do the same process. Instead of doing the division, you have to do the multiplication by the bases. And you have to consider the carry for finding the result. Otherwise, you can consider it as an integer part. While doing the division, reminder is very, very mandatory. Okay, this is the one point you have to remember. Okay, right. So in the first example, we will check how to convert the decimal to binary. Okay, so the source is decimal, the destination is binary. So the binary is the destination where the base of the destination is 2. So what you have to do? You have to do the continuous division of the decimal number by using the 2. Right? In the step 1, 105 is divided by 2, the way quotient is 52 and the remainder is 1. Next quotient is 52. 52 divided by 2, the quotient is 26 and the remainder is 0. In the step 3, the next quotient 26 divided by 2, quotient is 13 and remainder is 0. In step 4, the quotient 13 divided by 2, the remainder is 1, the quotient is 6. Next step 6 divided by 2, 3, remainder 0. Next step 3 divided by 2, the quotient is 1 and the remainder is 1. In the next step 1 divided by 2, 1 divided by 2 is indivisible. So quotient is 0 and the remainder is 1. So as I said, if you want to convert the decimal to binary, decimal should be divided by the destination base. So the destination base is 2. We did the continuous division. Next you have to ensure the reminders available. So reminders I ensured. Here kindly remember one thing. While writing the reminder, you have to follow the bottom top approach. So the bottom number should become first. So 1, 1, 0, 1, 0, 0, 1 base 2. Right? So you already know what is LSB and what is MSB. So what is LSB? LSB is nothing which is the rightmost bit. What is MSB? Which is the leftmost bit. So I represented in the quotient column as, please check the quotient column. In the quotient column, I represented it as MSD and LSD. So MSD, which is the last reminder, LSD, which is the earlier reminder. So this is the way how you have to convert the decimal number to binary number. Next, check how to convert the decimal number to octal number. The procedure is same. You have to divide this decimal number by using the destination base. What is the destination base? Which is 8. So 378 divided by 8 is 47 and the remainder 2. In the next step, 47 should be divided by 8. So 8 fives are 40. The remainder is 7. So the next quotient is 5 divided by 8, which is indivisible. So the quotient is 0 and the remainder is 5. Already you know what you have to concentrate. You have to concentrate only your remainder. But how you have to write the remainder? From bottom to top. So the first number is 5, the second number is 2 and the first number is 5 and the second number is 7, the third number is 2. So that is 5, 7 to base 8. So 2 is nothing which is a position 0. Next it is 7 is position 1 and 5 is position 2. Right? So 5 acts as a most significant bit and 2 acts as a least significant bit. In the example 3, we will discuss how to convert the decimal to hexadecimal, right? So I am taking the number 1000. So 1000 is a decimal number. So you have to convert it into hexadecimal. Hexadecimal is a destination, right? So the destination where the base is 16. So first step, 1000 should be divided by 16. Quotient is 62 and the remainder is 8. In the second step, 62 should be divided by 16. Quotient is 3 and the remainder, please remember, it is 14 because 16 into 3, 48. 62 minus 48, the resultant remainder is 14. But you already know in the hexadecimal number system, there is no numbers from 10 to 15. Instead of that, you have to append it as A to F. So instead of 14, I have written it as E there. In the third step, 3 should be divided by 16, which is undivisible. 0 is a quotient and 3 is a remainder. How to write again? From bottom to top. So the most significant bit is 3, the next bit is E and the least significant bit is 8. So this is the way how you have to do the conversion of decimal to binary, octal and hexadecimal. Right? In the next example, we will see how to work it on the fractional representation. What is a fractional representation? It is a decimal point representation. So convert 0.375 base 10 to binary. I have given you the notification earlier itself, right? What is the notion I told? If you want to convert the fractional part to other bases, you have to do the multiplication by the destination base. So what is the destination base here? 2. What you have to do? You have to do the multiplication of 0.375. So the step 1 is 0.375 into 2. So the resultant is 0.75. See, this dot represents the radix point or decimal point. Okay. After the decimal point, we used to call it as a fraction. Before the decimal point, we used to call it as an integer or carry. So carry alone you have to consider. So the carry here is 0. What is the next fraction? 0.75. So 0.75 into 2. The value is 1.5. So the integer part or carry part is 1. Again the fractional part is 0.5. So 0.5 into 2. Again what is the value you got? 1 dot of 0. So 1, which is your integer part or carry part, 0. So if 0.0 divided by multiplied by 2 or divided by 2, nothing will happen. So I stopped there. Okay. But while writing the result, you have to do the top to bottom approach. So your top value is 0, next value is 1, the last value is 1. So the value is 0.011 base 2. This is a conversion of decimal to binary. Right? Next you have to do the decimal to octal. Again the procedure is same. This decimal fraction should be multiplied by 8 because base of the octal is 8. So 0.6875 into 8, result is 5.5. Take over the carry or integer part to the consideration 5 and the fraction part 0.5. So 0.5 into 8, which is 4.0. Consider the fractional part 0. 0.0 into 8 is again 0. So the third step I didn't follow. In the second step, I have to consider my integer part or carry part, which is 4. How to write the result? From top to bottom. That's why I have written it as 0.54 base 8. So the third one is again decimal to hexadecimal. Means this decimal fraction again should be multiplied by the destination's base. Destination's base is 16. So 0.65625 into 16. The value is 10.5. Right? in the integer part or carry part, you have the value of 10. In the hexadecimal, you already know there is no 10, but the 10 should be written as A. That's why I have written it as A. Next fraction is, in the same result, the fraction is 0.5. So 0.5 into 16, which is 8.0. 8 is the applicable value there in the hexadecimal. So I have taken that integer part or carry to the next side, and again my fraction is 0.0. 0.0 into 16, again it is 0. No need to continue. How to write? You have to write from top to bottom. So that is 0.8 of 16. So that is a conversion from the decimal to hexadecimal. One thing remember, please don't forget to mention the radix point while you are using the fractional representation. Right. So in this section, we are going to check other bases to decimal. Okay. For other bases to decimal, the shorthand or shortcut, the fastest representation, I will tell you what you have to do. So other bases to decimal, you have to consider the face value and positional value. Otherwise, place value. You have to multiply this two and you have to add the forthcoming numbers available there. So here I mentioned the positional weight, which is nothing. Multiply every digit by its place value and sum that value. We will see how things are happening. So first, binary to decimal, right? Because other bases to decimal. What are the other bases except the decimal? Binary, octal and hexadecimal. We will see one example per representation, right? So convert binary to decimal. Are you accepting that it is a binary? Yes, because it is a combination of zeros and ones. 1, 1, 0, 1, 0, 0, 1 of base 2, right? You have to convert this binary to decimal. The same I have represented here, 1, 1, 0, 1, 0, 1, 1. See, check here, near to the base, I have 1. So that is my bit 0. Next one, it is bit 1, bit 2, bit 3, bit 4, bit 5 and bit 6. So bit 6 is again the 1, but that is farthest from the base representation. So means that is your MSB, and the least representation is, so the farthest is a MSB and the least one, which is your LSB. Okay, right. We will see what it is happening. See, already as I said, it is bit 0, bit 1, bit 2, bit 3, bit 4, bit 5 and bit 6, right? Okay. And one more thing you know, that is a binary system which is having zeros and ones. So 1 represents that it is a on state, 0 represents that it is a off state. Okay, right. So the first bit, bit 0. So how to write the position? It is 2 power of 0. Why we are writing 2 power of 0? Because the source base is 2. 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5 and 2 power 6, right? So 1 into 2 power 6, 1 into 2 power 5, 0 into 2 power 4, 1 into 2 power 3, 0 into 2 power 2, 0 into 2 power 1, 1 into 2 power 0. 2 power 0 is 1. So 1 into 1 is 1. Next check 2 power 3. 2 power 3 is 8. 8 into 1, 8. Next 2 power 5. 2 power 5 is 32. 32 into 1, 32. 2 power 6 is 64. 64 into 1, 64. So the values are 64 plus 32 plus 8 plus 1. So the way, what is the decimal representation you got? 105. Right? If you want to convert the octal, because what is our topic? Other bases to decimal. Now we are going to convert the octal into decimal. What are the octal values I have taken? 572 base 8. So you already know Octal values are representing between 0 to 7. So here also, what are all the things you have to consider? Phase value and place value. What are the phase values? 5, 7 and 2. Already I have written. Next you have to consider the place value. What are your place values? 2 is 8 power 0. The place value of 7 is 8 power 1 and the place value of 5 is 8 power 2. So 8 power 2 in the sense 16. 16 into 5 plus 8 power 1 in the sense 8. 8 into 7, 56. And the third value is 2. 2 into 8 power 0, 1. 2 into 8 power 0. 8 power 0 is 1. So 2 into 1, 1. So 2 into 1, 2. 8 sevens are 56 as well as 8 power 2, it is 16 into 5. So the result is 378 in decimal. Next, what is the one more conversion? Yes, absolutely it is hexadecimal to decimal because that is a third base. So hexadecimal to decimal. See, the value I have taken is 3E8 of 16. E is available here. So means that surely it is a hexadecimal only. Here again what you have to do? I have to take the phase values as 3E and 8 and place values as 16 power 0, 16 power 1 and 16 power 2 as usual. 16 power 2 into 3 plus E into 16 power 1 plus 8 into 16 power 0. Try to recollect. E is nothing which is value 14. So 14 into 16 power 1. The result I am getting it as 1000. 1000 in decimal. So in the second we converted other bases to the decimal. Okay. Now we will check what will be happening for the fraction. Again, binary fraction to decimal, octal fraction to decimal as well as hexadecimal fraction to decimal. So what is the first value we have taken? First problem 0.011 base 2 to decimal, right? 0.011 base 2 to the decimal. I hope you remember that in the radix point, before the radix point you have some values and after the radix point you have some values. Before the radix point, the values and all we used to term it as an integer part. After the radix point, we used to consider those values or the fractional part. In your module 18, I told integer part, it is a positive power. If it is a fractional part, it is a negative power. Already we discussed that. So based on that, here you have to apply. So 0.011. What is the value you have to consider? After the fractional point. I mean after the radix point, you have to consider the fractional. 0, 1, 1. So what is that 0? 2 power minus 1. What is that 1? The position value is 2 power minus 2. And the last one is 2 power minus 3. Right? Phase value is 0, 1, 1. And the place value or positional value or else weight, that is 2 power minus 1, 2 power minus 2 and 2 power minus 3. How to write 2 power minus 1? It is 1 by 2. How to write 2 power minus 2? 1 by 2 power 2. How to write 2 power minus 3? 1 by 2 power 3. Right? So 1 by 2, which is 0.5. 1 by 4, 0.25. 1 by 8, 0.125. What you have to do? You have to multiply the phase value as well as your place value. 0 into 2 power minus 1, 0. 1 into 2 power minus 2, that is 0.25. And 1 into 2 power minus 3, 0.125. So by adding these three, the result is 0.375 in the decimal representation. Okay? Yes, as usual, you have to do the same representation for octal. So the example we have taken is 0.42 base 8. So what are the phase values you have to take? 4 and 2. Place value is 8 power minus 1 and 8 power minus 2. So 1 by 8 and 1 by 8 power 2. Right? So 4 into 8 power minus 1 plus 2 into 8 power minus 2. How to write 8 power minus 1? 1 by 8. How to write 8 power minus 2? 1 by 8 square. So the resultant is 0.53125 in decimal. Next, hexadecimal fraction to decimal. The values we have taken is 0.D216 to decimal. That is the conversion you are going to check, right? 0.D to base 16. So you have to consider the face value and place value. Face value is D and 2. Place value is 16 power minus 1 and 16 power minus 2. D into 16 power minus 1, 2 into 16 power minus 2. Again, please recollect, D is nothing, which is a number 13. So 13 into 1 by 16 plus 2 into 1 by 16 power 2. So the resultant is 0.8203125 in decimal. This is the way how you have to convert the fractional part to the decimal value. It may be the binary, it may be the octal, or it may be the hexadecimal, right? In the section 3, you are going to check what are the conversions happening between binary to octal and binary to hexadecimal, right? This one already I introduced you there in your module 18. In the module 18, I told binary is a combinations of zeros and ones. So what is the relationship of octal with binary? It is 2 power 3. What is the relationship of hexadecimal to binary? It is 2 power 4. Here I represented octal is 8, which is 2 power 3. Hexadecimal is 2 power 4, 16. So this is the way how you have to group the bits, right? If the binary group as 3 bits, we used to call it as an octal. The same binary group into 4, we used to call it as a hexadecimal. The first problem is convert 1101011 base 2 to octal. So base 2 I represented. So means that surely it is a binary. You have to convert it into octal. What is the relationship between binary to octal? Binary grouped as 3 bits. That is defined as an octal representation. Okay. Here 3 points you have to remember. Point number 1. Whenever you are grouping, consider whether you are grouping in the integer part or you are grouping in the fractional part. Point number 2. While grouping, you have to consider the grouping either from the radix point towards the left side, otherwise the radix point towards the right side. Point number 3. If you have any shortage of bits there in the grouping, it is must that you have to append the zeros. So these 3 points you have to remember before solve the problem, right? We will see what is happening here. So check this problem. Is there any radix point? No. If there is no radix point, you can surely say that it is only the integer part. Otherwise, it is only the real part. Okay. If it is a real part, you have to do the grouping from the LSB towards MSB. So what is your LSB here? 1. Because that is bit 0. So the next value bit 1, face value is 0. Bit 2, the face value is 0. So the first grouping is 0, 0, 1. Take down the next grouping. 1, 0, 1. What is the third grouping? 1. Right? But you have to do the octal grouping. If it is octal grouping, how many bits you needed? 3 bits you needed. But for this particular MSB, there is no 2 other bits. That's why I am appending or padding 2 zeros. So the way the first value is 0, 0, 1. The second grouping is 1, 0, 1. And the third grouping is 0, 0, 1. I hope you remember what is the weight code you have to follow for octal. The weight code you have to follow is 421. So check your first value 001. In the 001, 4 is 0, 2 is 0. The weight is applicable only to 1. That's why I have written 1 there. In the second grouping, it is 101. 4 is 1, as well as 1 is 1. So 4 plus 1, 5. In the third grouping, again 0, 0, 1. 4 is 0, 2 is 0, 1 is only 1. So the resultant is 1. So what is your octal representation? 1, 5 and 1. So I have written it as 151. In the next one, I am converting the same number, whatever we discussed in the earlier problem, binary to the hexadecimal. What is the relationship between binary to hexadecimal? 2 power 4. So how many groups you have to do? Based on 4 bits you have to do the group. Okay, right. So what is the name of that 4 bits? It is a nibble. So you have to group as a nibble. Again, here check the first one. What is the first point you have to check? Whether it is a real number or else it is a fractional number. It is a real number. If it is a real number, how to start the grouping? You have to start the grouping from the LSB. LSB is 1. The next value is 0. Next value is 0. The next value is 1. So the way I have written it as 1, 0, 0, 1. You can see the group. Check over the next group 0, 1, 1. 0, 1, 1 is there, but already I told nibble in the sense surely it should have 4 bits. So 1 bit is missing. So what I did, I am padding a 0 there, right? So 2 groups are there. So if it is a hexadecimal, what is the weight code here? 8421. So check your first representation. I mean, in your LSB side, it is 8421. 8 is on as well as 1 is on. Because 8 is having the value 1 as well as 1 is having the value 1. So 8 plus 1, 9. In the second group, check whether 8 is 0 as well as 1 is 0. But 4 and 2 are on. What is 4 plus 2? It is 6. So what is the value you got? 0, 1, 1, 0, 6 and 1, 0, 0, 1. It is 9. So what is the resultant you got? 69 in a hexadecimal representation. Right? Okay. Right? Now check the binary fraction as well as the hexadecimal fraction. Right? Binary fraction to the octal as well as hexadecimal. Right. Okay. Right. In the binary fraction. So fraction in the last example, last 2 examples, it is a real part. In the real part, have you considered? You grouped from the LSB towards MSB, right? If it is a binary fraction, please do the grouping from the highest bit to your lowest bit. I hope you remember, right? What do you remember? After the radix point, the first value is the highest value. You can write it as minus 1. The next value is minus 2, least. The next value is minus 3, least. The next value is minus 4, least. So you have to do the grouping from the radix point outwards. Right? There you have to do the grouping from the radix point to left side. But here you have to do the radix point to the outward. Okay, right. Here also, if you have some shortage there in the group, you have to append zeros. So consider the positional value 2 power minus 1, 1, 2 power minus 2, 0, 2 power minus 3, 1. So 1, 0, 1. It is an octal. So I grouped. In the next one, I have only 1. But if it is an octal, I need 3 bits. So I have appended 0, 0. Right? So 101 as well as 100. Already you know the code you have to follow is 4 to 1. 4 is on as well as 1 is on. So 101 is 5. Here 4 alone is on. So the value is 4. So the octal representation is 54. But you are doing it for the fraction. That's why I have written it as 0.54 base 8. Otherwise radix 8. Next, we are trying to do for the hexadecimal. Again in the hexadecimal, the first place near to the radix point is minus 1, minus 2, minus 3 and minus 4. So till minus 4 I am grouping 1101. So minus 5, 0, minus 6, 0, minus 7, 1. But minus 8 I don't have. But I have to do it as a hexadecimal. Means that I need a nibble. If I want a nibble, I have to append 1 0. So I have appended 1 0 outwards of my radix. Now check how many groups you have. 2 groups. 1 1 0 1, 0 0 1 0. So the code you have to follow is 8 4 2 1. So here 8 on, 4 on as well as 1 on. So 8 plus 4 12, 12 plus 1 13. How to write 13? D. Next it is only 2 is on. 8 4 2 1, only 2 is on. So the value is D2. The result is D2. But it is a fraction, so I have written it as 0.D2 base of 60. Right? Now check whether octal and hexadecimal to binary. Right? You have to convert octal and hexadecimal to binary. Again, the trick is same. If it is an octal, it is of 3 bits. If it is a hexadecimal, it is of 4 bits. Right? So means that each digit in octal should be represented by using the particular word length. What we discussed there in the module 18 of the slide 2. There I specified finite word length. What is the finite word length? The number of bits available there in the register. If it is an octal register, the number of bits should be 3. If it is a hexadecimal, the number of bits should be 4. That is a nibble, right? So we will do that conversion, octal to binary. Consider the example 572 base 8. So 572 base 8 automatically shows that it is an octal number. What is the octal number for 5? You have to follow the 4 to 1 code. So 4 and 1 should be on, 2 should be off. So the value is 101. What is the second number? 7. So 4, 2, 1 should be on. So the value is 111. What is the third number? 2. 2 alone should be on, other value should be off. So for 5, 101. For 7, 111. For 2, 010. So while writing, what is the resultant you got? 10, 10, 11, 11, 010. Right? Right. So next we will check hexadecimal to binary. So if it is a hexadecimal, how many bits you have to represent? 4 bits you have to represent. So what you have to use? You have to use 8421 code. Take the example 3E8. So how to write 3? 8 should be, the weight of 8 should be 0, the weight of 4 should be 0, the weight of 2 and 1 should be 1. So the value is 0011. What is E? E in the sense it is 14. So 8, 4, 2 should be on and 1 should be off. If it is 8, 8 should be on and other value should be 0. So for 3, it is 0011. For E, it is 1110. And for 8, it is 1000. So how to write that? 0011, 1110, 1000. This is for the hexadecimal to binary conversion. So one thing you should remember is fixed with. Next, octal to hexadecimal, right? Octal to hexadecimal. What is the octal number they have given? 572 base 8. You have to convert it into hexadecimal. Here, you have to follow the steps, right? Right. In the step 1, you have to convert the given octal number to binary number. In the step 2, the binary number should be grouped as a hexadecimal number. So here, binary is a bridge between octal to hexadecimal conversion. We will see one by one. In the step 1, first you have to convert the octal number to binary number, that already known by you. 5 should be considered as 101, 7 should be considered as 111 and 2 should be considered as 010 based on your 4 to 1 code. This is your first step. 5 is 101, 7 is 111 and 2 is 101. Now you have to write that number continuously. 1011111010 base of 2. This is your binary. This binary should be converted to hexadecimal in your step 2. In the step 2, what you have to do? This binary should be considered to hexadecimal. As I said, the first point you have to check whether it is an integer part or fractional part. It is an integer part. If it is an integer part, second step what you have to do? You have to do the grouping from the LSB towards MSB. Third part what you have to do? You have to write the hexadecimal representation. LSB starts at 0 followed by 1, 0, 1. So 1, 0, 1, 0. That is your first group. The second group is 1, 1, 1, 0. The third group is 1 alone. So if 1 is alone, you have to make it as a nibble. If you want to make it as a nibble, what you have to do? You have to do it as 3 zeros should be appended. So 0001 based on 8421 code, the value is 1. 0111, it is 7. Next it is 1010. 1010 is 10. There is no 10 here. Instead of 10, you have to write it as A. So what is your resultant now? 17A base 16. So you have converted the octal to hexadecimal here. Right? So it is a simple and quick references whatever you learned in the earlier slide. In the first slide, what you learned? How to convert the decimal to other bases. So if it is a decimal to other bases, two things you have to remember. If it is a real part, you have to do the continuous division and you have to check over the remainder, and the remainder should be written or read bottom to top approach. If suppose it is a fraction to other bases, multiply each fraction by the bases, and you have to check over the carry or integer part. Those should be read or write as a top-down approach. If you want to convert other bases to the decimal, you have to follow only one step. You have to do the multiplication or product between the digit as well as the bases, and you have to do the sum for every term. If it is a binary to octal or hexadecimal, the grouping is mandatory, because octal it is 2 power 3 as a representation 8, hexadecimal 2 power 4 as a 16. Here binary is a bridge between these conversions. This is a simple and quick references for the earlier part. So decimal to base, fraction to base, base to decimal, as well as binary to octal and hexadecimal. Based on these classes, it is easy and possible for you to do the conversion between any two bases, maybe from binary to octal, otherwise octal to decimal, otherwise from the decimal to hexadecimal, or it may be any way, right? The things you have to remember is where you have to do the division, where you have to do the multiplication, where you have to do the grouping, where you have to use the binary as a bridge. I hope you can able to understand this session. If you have any doubts or any queries, please post it in the comment box. The answers will be taken by you so soon. Thank you. Thank you for this session listened by you. Thank you.